and get started. So good afternoon, good morning, good evening, wherever you are in the world. My name is Julia Matevosyan. I'm Chief Engineer at ESIG. I would like to welcome you all to our 2022 ESIG monthly webinar series and give you a little bit of background on ESIG. For those of you who are not familiar with ESIG, we are a membership-based non-profit organization providing our members with objective information, resources, and networking opportunities in support of energy transition. We do this through workshops, tutorials, webinars, blogs, working groups, and task force activities, and producing technical resource materials. ESIG also serves in a leadership role in Global Power System Transformation Consortium, the GPST, whose mission is to bring together key actors to catalyze a rapid clean energy transition at unprecedented scope and speed. ESIG leads Pillar 1 of the 5 pillars, which deals with research agenda for the system operators. You can find more information on GPST at www.globalpst.org. We're also currently busy in preparation for our regular meteorology and market design for grid services workshop, which will be held week of June 6th. And this time, in parallel with this workshop, we are also holding a special topic workshop on grid forming inverter-based resources. You can see currently on the slide, you can see high-level agenda for both workshops, as well as links for registration on the slide. And also Ryan Willis will link up, will send those links in the chat. So you can click on the link and have more information. Our workshops and monthly webinars are open to everyone, so please feel free to register anytime on ESIG website. If you're new to ESIG, I strongly encourage you to follow up with us. If you like what you hear in the webinars and workshops, and I think you'll be pleasantly surprised. ESIG membership will give you an opportunity to participate actively in all of our working groups and task forces. You can find us on web at www.esig.energy, as well as LinkedIn, Facebook, Twitter, and YouTube. Okay, a few logistical matters before we get started. All the phones will be muted for the duration of the webinar to avoid any unnecessary distraction. For Q&A, we're using Slido platform. So to ask any questions, please go to slido.com and enter ESIG24 as an event code. The instructions are also at the bottom of the screen. Well, you'll see, and you'll see a code in the chat window as well. You can use thumbs up next to questions to cast your vote and help prioritize questions that have already been submitted. We plan to have about 10-15 minutes for Q&A at the end, and then we'll wrap it up at the top of the hour. An email with a link to the recording will be provided after the video is ready. We also plan to provide short responses to all unanswered questions after the webinar. So please don't be afraid to ask your questions on Slido. So today's topic will be EMT modeling and simulation. Who needs an EMT model for doing stability studies? This webinar will focus on why, when, where, and who questions for as far as wide area EMT modeling is concerned. A brief discussion on how question will also be presented. I feel fortunate to have Babak Badrzadeh here with us today. Babak is both professional colleague and a good friend. We have collaborated on renewable integration topics for many years through SIGRE, IEEE, and ESIG activities. Babak holds BSc, MSc, and PhD, all in areas of electric power systems. Prior to joining Aurecon in March 2021, he was with Australian electricity market operator as a manager of operational analysis and engineering team. He is currently technical director of power systems with Aurecon and is an adjunct professor with Monash University. His focus area is power systems modeling and analysis, including impact of transmission connected and distributed inverter-based resources. Babak has played a key role in worldwide establishment of wide area EMT modeling and the overarching area of system strengths. I greatly value Babak's contribution to ESIG and the industry, and I look forward to what he has to share today. Following Charlie's tradition, I actually went ahead and checked on LinkedIn, and I'm happy to report that we have 263 common connections on LinkedIn, working with many of the same people over the years. I consider Babak a good friend and good friend of ESIG, and it's a pleasure working with him. Just a short reminder once again that we are using Slido for questions with the event code ESIG24. And without any further ado, let's go ahead and get started. Babak, I'll now turn over to you.
Hi everyone, thank you Julia for the very kind words. So it's a pleasure to be here again after a while, and let me get straight to the... Okay, so what I'm actually going to put out maybe is a little bit unusual style, but this is what I'm actually hoping we achieve at the end of this presentation, that we can answer this question more confidently, because there are different schools of thoughts in the industry and different countries, and many friends and colleagues that I have been dealing with. So there is one school of thought that EMT modeling, especially moving forward, should be used for all applications when it comes to stability studies. And the other school of thought is that perhaps these modeling impractical to use, or we can get the traditional phasor-domain modeling as good and accurate as EMT modeling. And the last is somewhere in between, that maybe there are horses for courses. We can use each to its strength. So let's continue. Hopefully by end of this presentation, we can uncover this a little bit better. I have been this is actually the third time that I have been requested to make a presentation or write up on the same topic. The previous two times were in 2019 and 2020, where I was with AIMO. And I note that coincidentally, all these timing have been similar for most of you that are based in North America. That's around the summer. That's why I tend to think that maybe there is a good reason for this coincidence, and I'm calling it EMT season. But on a more serious note, it's also a great opportunity for myself actually to reflect on what I have learned since last time. That was nearly 2 years back. So what I would like to cover, as Julia already mentioned in the introduction, is that focusing primarily on the why element, why someone might need EMT modeling for stability studies, and then looking at when, where, and who. I would not be covering the how element in great detail, but I will refer you to other work that in being done in industry that you can refer, and more than happy to answer any question it comes. But I just wanted to keep this at relatively high level so that we won't go to the how element. Now, more specifically, what we're going to cover in today's webinar. So one of the first thing that I would hope to achieve is a factual and unbiased comparison of phasor-domain and EMT model to their strengths and weaknesses, and then narrowing down more specifically on the key value propositions of EMT modeling, not just for the system as is, but the system that we're going to transition in next decade or couple of decades where there won't be any synchronous generators by which time. And then trying to investigate a little bit if there are criteria and conditions that could educate us to more deterministically and more judiciously decide under which condition it would be prudent to use this type of EMT modeling. A brief discussion on the comparison of vendor-specific versus generic EMT models, and especially how this could evolve and will evolve moving forward. Again, like I said in the previous slide, we won't be talking much about the how element. There are two very key aspects which won't be covered here, but this is part of the secret working group C456, which will be published shortly, and I had the privilege to convene this working group. These are on model validation and essentially how to develop systematically these wide area EMT models. And an evolving topic, which is more of a work in progress, hopefully within next 12 months, there are more concrete answers to this question, is that how the offline or the type of EMT modeling which is primarily used currently in the industry compare against the real-time EMT modeling. Now, this is a personal story, and I would like to be as brief as I can because I don't want to present information about myself, but I'm using this as an example of how someone like myself started its career, like say 20 years back, and almost every year I have been dealing with multiple applications. Here I've listed the key ones that I started and how it has been evolving. So essentially this is the journey that I would wanted to share with you rather than what I have been doing specifically. As you can see, starting from say 2007, so these are the classic application of EMT modeling. You're looking at subsynchronous resonance, torsional interaction, harmonic resonance, then developing like EMT model for a manufacturer, doing installation coordination studies, uh, early days of using real control codes in the model, which is now becoming a norm. Again, subsynchronous control interaction, the ones that occurred in 2009 in Texas. And you can see that gradually moving to more system-wide studies like black start studies, commutation failure for HVDC link, and all of a sudden we have in 2016 South Australian blackout, which was a catalyst to essentially signify the importance of this type of models and what accuracy gain we could have, especially in future power systems, because back then there was not necessarily a significant penetration of inverter-based resources. And as it has been evolving over this past or six or 7 years, I would say, it has been primarily shifting towards the use of EMT modeling, not for its classic applications, but for stability analysis, where often the focus is the behavior around the fundamental frequency. And these days also the topic of subsynchronous interaction returning in a different way compared to what we used to look into a decade or 2 decades ago. And the last point I want to mention is that the two boxes that I highlighted in blue color. So these 2 years, I was just looking back and there was not a significant EMT activity that I had been involved. But then I was looking at, and maybe that was a coincidence, but important topic, which unfortunately I won't have time to discuss for today, is the technical requirement. So the 2 years that has been quieter, I realized that we were basically working on developing the technical requirements and providing guidelines and guidance as to how this type of studies can be done, what level of detail the models will need to have. If there is any question, again, more than happy to take. Let's start with comparison of EMT against phasor-domain modeling. I'll start with a very basic RL circuit. And obviously, as we remember from the electric circuit that we studied in undergrad degree, we can represent that with a differential equation, or it can be simplified in a phasor domain representation that we can see here. And this is essentially the basis and the differentiator between the EMT and the phasor domain modeling, which as you can see, I'm introducing a new abbreviation, calling it PDT. I will have a brief discussion in this slide as to why we basically using PDT as opposed to RMS. So with electromagnetic transient simulation, they based on the actual waveform, as you can see here, three-phase waveform, which prior to the disturbance, it's sinusoidal, three phases 120 degrees apart, and as the fault happened, that symmetry cannot be maintained anymore. On the other hand, the phasor domain modeling is not based on the instantaneous values, but the phasor domain, which you can see an example of it in this very simplified circuit. And unlike the EMT modeling, which solves the differential equation, such as this that we have here, the phasor domain is based on algebraic equation, which you can see here. The other difference is that the waveforms by default will retain not just the fundamental frequency components, but also the harmonics and interharmonics, whether below the fundamental or above the fundamental, whether it's several kilohertz. And because of these two reasons, first solving differential equation, and second retaining all these components, this type of modeling is slower. On the other hand, phasor domain modeling does not account for harmonics, and that coupled with solving phasor domain as opposed to differential equation make this type of simulation faster, and that's sometimes faster, sometimes much faster, depending on what size of the system we're looking at and what level of detail is included in the EMT modeling. Before we leave this slide, as I promised earlier, just wanted to uncover this term RMS that I have also been using for a while, basically, and whether this is the correct representation of what we actually alluding to. So as we all know from, again, electric circuit theory, RMS calculation is performed to basically achieve a single value for a time varying waveform with respect to the time. This is not exactly what we're trying to do here. So it's a subset because when we're talking about phasors, they have magnitude and phase angle. And that's for this reason, the correct, more accurate term is phasor domain modeling. And just to make sure that we're not using basically RMS, we came up in the secret working group the terminology or acronym of PDT. Okay, what details are excluded in phasor domain modeling and how important they are? So that's what we're going to look into in the next 5 slides. So the first thing is the instantaneous values we already discussed in the previous slide. So if you remember the comparison of this graph against this, in the phasor domain modeling, we're not looking at instantaneous values. So that's hopefully clear. Harmonics and interharmonics, we already discussed about that. Asymmetries, whether asymmetries in a steady state condition or those asymmetries that are exacerbated during the fault conditions. And last but not the least are fast controllers. The two components which I'm going to discuss in more detail are the instantaneous values and the fast controllers, why they could be important for analyzing a power system with many inverter-based resources. To answer this question, let's start from the basic principles. How does an actual IBR and its control operates in power system before we're going to discuss what is the best way of developing a mathematical model, how the actual IBR operates, and what are the physics around that. In a steady state condition, like I mentioned in the previous slides, voltages and currents are perfectly sinusoidal. Again, let's assume that there is no steady state asymmetry. Let's make the situation simpler. In this case, the three-phase current or voltages would be perfectly sinusoidal and with 120 degrees separated from each other. Now, if a fault or disturbance happens in the system, this sinusoidal relationship does not apply anymore, and therefore the term phase angle that we use and on everyday basis does not have its usual meaning. What it means and why is that it's because the three-phase currents and voltages should be considered individually because we don't have the sinusoidal relationship anymore. And this has to be done on instantaneous basis. Again, I remind you of this waveform. As you can see that the values are not the same. So when it was a steady state, whether you take say t1 second or 1.2, the values are not going to be different. But during the fault and after the fault recovery, the values won't be the same at any given point in time. And this is the reason that we need to, or not we, actually the actual equipment need to look into these individually and instantaneously. And if you're dealing with something like a wind turbine, then there is also interaction between the rotor circuit and a stator circuit and how that can be accounted for. So there is interaction between the three phases, regardless of which quantity you look into, and then additional layer for a wind turbine or electrical machine, basically, the interaction between rotor and a stator. So what this means is that besides the magnitude, besides the phase angle, there is effectively a third dimension that would need to be taken into account. And this is the instantaneous position of the current voltage or flux if there is an electrical machine. So what we are getting from this slide is that the actual equipment would work with the instantaneous value, would need that, the instantaneous position would need that in addition to the magnitude and phase angle in order to see what is happening in the external world and how it should respond and how the control system should be designed and tuned. So let's go into one extra layer and look into the importance of this instantaneous position in greater detail. I've tried here to simplify the concept of reference frame transformation, which is what we basically know in the industry by Park and Clark transformation that I've tried to highlight in this graph basically. Assuming that we have a three-phase sinusoidal voltage or current, the Clark transformation will make that two still sinusoidal and AC waveforms, and then with Park transformation, you will create two DC components as if we are converting the three-phase system into a separately excited DC machine, basically. The advantage of this is that the control of active and reactive power can be largely done independently without interfering each other. And this is all done by the likes of Park and Clark transformation, which Park transformation is the more general transformation. If you make the angle theta 0, that would make it Clark transformation, which is what we have basically here. What is the importance of this angle? Essentially, this is the very job that phase lock loop or PLL will need to perform, and to basically does this job and instruct the rest of control systems within the inverter control. This instantaneous position or the theta angle that we discussed is important. So this is still nothing to do with the model. It's just the reality of how the equipment behave. Should we capture everything that equipment require, or should we not? And again, there are horses for courses, but this is the basic principles of how most inverter-based resources in the market operate. Now, here I'm not basically trying to discuss in great detail about the differences between grid forming and grid following inverters as a separate topic, and I will have a brief discussion on this in 2 weeks' time in the EC workshop that Julia mentioned. But without going through detail of each of the grid following or grid forming inverter, What I wanted to share with you is that the most practical grid following and grid forming inverters have one thing in common, that both comprise of outer loops and inner loops. Whatever they are, we are not really interested at this point. And similarly, grid forming, outer loop, inner loop. Whether grid forming inverter emulate performance of a synchronous machine, and to what extent, is not really the point for discussion, and that's why it is important when we trying to determine the suitable level of modeling and suitable approach for modeling, whether grid forming or grid following, they will basically follow the same approach. And noting that typically there is a factor of 5 to 10 times difference between the frequency or the clock speed for the controls of inner loop and outer loop. Just say, for example, if inner loops run at 10 kilohertz, which is the switching frequency of PWM, the outer loop could be somewhere like 1 or 2 kilohertz, basically. Okay, so now we basically know the absolute frequency of the grid and the frequency of different phenomena. We also know the switching frequency of the PWM strategy, which is in the range of kilohertz. But let's bring another type of frequency into the picture, which is less widely used, but it is important because that would allow us to compare the performance of phasor domain against EMT modeling. For simplicity, let's take a first order system, a first order lag, or a PI control, which is the basis of most controls in the system. And for the time being, let's assume that we're taking this 10 hertz bandwidths completely arbitrary. But in the next slide, we discuss that this is not really arbitrary. So it has a significance. And what we're trying to do here in this slide to bring in the third element, which is the bandwidth and what it means, and it make it easier for us to compare the performance of the RMS and EMT modeling in terms of level of modeling detail, basically. If I'm basically trying to calculate with a given bandwidth of 10 hertz on a 50 hertz system, which is something that I live with. That gives me a 16 millisecond time constant, which means that if we're really trying to account for time constants are shorter or much shorter than 16 millisecond, that may not be really practical. The other point that we get from looking at this slide is that if we have a bandwidth of 10 hertz, then assume that we have a signal which is 100 hertz. Okay, so what basically this tells us, based on known mathematics and the attenuation factor of minus 20 decibel per decade, the 100 hertz signal will be attenuated by a factor of 2, which means that essentially for a 10 hertz bandwidth, the 100 hertz signal would be nearly like a noise. Basically, it does not make sense of it. It would be attenuated quite significantly. Okay, so this is what we learned from the term bandwidth and what it means. Why we are interested in this 10 hertz bandwidth. Let's look into the next slide. So this is basically a known principle and stated in the user manual of most phasor domain tools, that they are typically suitable for a bandwidth of 10 hertz. They may be suitable for a little bit higher, but this is pretty much what is guaranteed. Now, what it means in terms of the impact on various control loops within an inverter-based resources, this is something that I have been presenting for more than a decade, basically, and I've seen it's been used elsewhere, so which make me happy that essentially other people might have find this to some extent useful. So what basically this tells us is that what we can confidently model in a phasor domain simulation which is within 1 to 10 hertz, this kind of phenomena. Whereas if we are looking at things such as control instability, so that is what we are interested, or if we noting that the PWM converters running at a few kilohertz, and that is what essentially the PLL and the fast current controls within the inverter-based resource operate. So these are type of things that as we start to model in a phasor domain simulation, they would need to be simplified and idealized because they cannot be modeled within what we can see in this green box. Basically, that's where we can model everything perfectly in the phasor domain simulation. As we go farther, it may not be possible. And historically, the impact of these faster controls have been insignificant. And also noting that some of these phenomena, for example, if you look at transformer energization, as I was mentioning in my personal story, so these are type of studies that have always been done in EMT. No one attempt to does that in phasor domain simulation. We can leave them out, but our interest really is on a stability analysis and what is the impact of this simplification and a bandwidth of around 10 hertz on what we can confidently model in phasor domain and what we may not be able to model. Okay, so I'm just presenting again a couple of examples, which I'm sure you have seen this a few times. Both this slide and the next is what I prepared in 2019. Again, it has been presented by myself and others in multiple instances, but just to close the loop, this is an example of what response we get from phasor domain and EMT simulation. And our focus is, I should highlight that on power systems with high share of inverter-based resources. This is by no means to suggest that phasor domain models are inaccurate in all instances. They have a strong basically place, but we are only focusing on power systems with a high share of inverter-based resources. What we see here, this is based on the wide area EMT model in basically practical part of the Australian power system, and this has been observed multiple times that essentially a fault happened. You can see that prior to the fault, the phasor domain and EMT show pretty much solid lines, the fault clear. You have a spike in the phasor domain model, which this is something I'm sure most of you have seen many times in your career. So let's leave this out. And this is basically has a solution. So good phasor domain model these days will not show this. But what is the more important one are these sustained oscillations, which will not damp. And this is what I was referring to, new forms and new manifestation of subsynchronous oscillations in the power system with high share of inverter-based resources and many of inverter-based resources in close proximity of each other with a dominant frequency of less than 10 hertz. Now, this is another example of looking at a classic HVDC link line commutated converter response to fault again. With phasor domain model, it recovered perfectly. With EMT model, it basically disconnects. So which one should we be relying to plan and operate the power system? Now, let's look into some of the emerging applications of EMT modeling for systems with high share of inverter-based resources. Let's narrow this more down so that we're not thinking of using EMT modeling for everything we do in our life, basically. So what are the applications that would warrant most attention? And what are the drivers for that? Like I said, what we are seeing everywhere in all continents is the changing power system with much higher share of inverter-based resources and simultaneous withdrawal of synchronous machines in the power system. And this has resulted in creation of new forms of system stability. And there is reasonable confidence that there are new forms of instability that we are yet to learn collectively as the industry. The second point, which is what I was alluding to from showing you the previous slide with regard to the HVDC system response, are what we have seen most often is that the overly optimistic response from the conventional phasor domain simulation. Another point that becoming more and more pronounced, and especially for you guys in North America have been doing good work actually already in some of these regards, is that historically we have been looking at system stability independently, and stability engineers are very different and have different skill sets to protection system engineers, for example. As the system moving towards very high or 100% renewable generation, the boundaries between stability, power quality, and protection are pretty much fading, and there are instances already where these are essentially highly intertwined with respect to each other. So you can't solve one problem without knowing the other. What also we can do is in countries like Australia, where I live and work, is a more certain, but of course a slower assessment of generator connection process, that you can identify a problem before it manifests itself in real system operation, which could result in a constraint on the generator that contributes to system instability. And also more certainty on the long-term planning of power system with understanding of the future system needs and equipment needs, basically, rather than just planning the system based on economical and resource adequacy analysis, what it takes to bring the dynamic system response when we're planning the system for next 10 or 20 years. And lastly, the very good point that the ESIG white paper recently published, which I had the pleasure to contribute, the chicken and egg status quo that was referred there, noting that the inverter-based resources are becoming more and more capable, and they can deliver different things to the system, but because they are current limited devices, they cannot deliver everything at the same time. So there are trade-offs and sacrifices, and what is needed by the real power system to which they are connected. And this is the real chicken and egg status, which with this type of modeling, we can basically address that to making sure that, for example, if you're talking about grid forming inverters, do they need to provide the same level of fault current as a synchronous generator does? Or maybe it's not any need actually, or if there is a need, why is that? Is that because of operation of protection relays? Maybe that can be handled differently. Okay, so let's talk at the when question. Historically, and again, I have been very proudly involved in 2013 and 14 as part of the worldwide development and consolidation of different forms of the short circuit ratio that has been documented in SIGRE Technical Brochure 671. And my friends in US in 2017 or 18, I believe, there was a NERC white paper, which is an updated version of that, that reflects on all these various forms. And while this has been really a significant development in terms of screening methods, where they fall short is that they are useful for when you know what problem you are looking for. But if we are looking at a system with 90% share of inverter-based resources, how do we know what we are looking for? And that's where we have the element of unknown. And a topic that I won't cover today, but I'm actually planning to cover this in my presentation in 2 weeks from now, is that how we can make the SCR methods suitable to represent truly the grid forming inverters, which are not the same as synchronous generators necessarily, despite having some of the stability contribution that a synchronous machine will have. And also to be conscious that we should not necessarily have a very weak grid to have interaction between inverter-based resources. A weak grid is just a catalyst to exacerbate the interactions rather than the sole condition. We have had also system non-synchronous penetration being used in islanded countries, but this is not applicable as it is for larger scale power systems, interconnected power systems. So how this question now evolving is that rather than using screening methods to say when you should or should not conduct EMT modeling, uh, to try more judiciously and efficiently decide how to run this EMT simulation less often, or reduce the number of scenarios that you will need to carry out. So I would definitely think there is a very strong place for the screening method, but perhaps to looking at it from a different angle rather than consider it as a black or white assessment that do EMT modeling or do not do EMT modeling. So moving forward, to me, EMT modeling are going to be essential, but obviously until the speed of simulation has been addressed, how we can make it more efficient and only select limited cases. On the comparison of vendor-specific against the generic EMT models, again, this is something that those of you based in North America know very well. The comparison between phasor-domain vendor-specific and generic models, without trying to repeat everything in this slide, how I would see the application and especially the emerging application of generic EMT models that historically, and I have personally been saying this and still I believe that, but now there is a very niche and very important application for generic models that historically vendor specific models have been used for power system operation and generator interconnection studies. This is where accuracy is very important, because you will either operate the system stably or unstably, and there's very narrow margins that sometimes we are dealing with. But being vendor specific by itself is not sufficient. So most often it needs to be site specific, especially when we're dealing with these very weak grid applications. For this situation, the use of generic model may not be the best choice, but it doesn't mean that generic models will not have a role to play. In my view, where there will be a strong application for generic models are for system planning studies. You're looking at 10 or 20 years. With a black box EMT model, you're not going to get really anything useful. And also, if you want to design conceptually a system and conceptually design an equipment, which is very different to how it is today, how are you going to achieve that with if it's with a black box model? This is where I will see a strong application and emerging application for generic models. Here I've spelled out only selected countries where whole system EMT modeling is already used, or partial modeling, and by no means trying to exclude any countries. So these are solely as an example. I appreciate that I have not necessarily captured every single countries. So like Australia, where I am, so we are basically modeling the or AMO, modeling the whole system with EMT simulation. Similarly in Belgium and France, and like of you in US, pockets of the country, some regions such as Texas or others with high share of inverter-based resources already being fully represented at EMT, but not necessarily every one of them. And to me, this is just a start of it. This will basically grow further and further. And lastly, what is next? Like I said, with the current speed of simulation, so these studies are good for looking at next few months or next few years, but even so, they're not really efficient. So a speed of simulation is definitely one point that will need to be addressed, and maybe part of this is maximizing the collective usage of phasor-domain and EMT modeling. And again, to reiterate, I will see that in next 10 years, 20 years, phasor-domain simulation will have a place, but maybe increasingly less often, and EMT modeling more often. I cannot see a future in next 10, 15, 20 years where we will be using EMT modeling only. Protection system integration, because of the interaction between stability, protection, and power quality, I already mentioned. Another point is more systemic development of boundary buses. This is sometimes done on trial and error. For example, if you are looking at stability analysis in California power system? Are you interested in Texas power system or New York, or how far would you go until you basically cut the system that you are modeling in EMT? Because the greater the model and the greater the number of dynamic models, the more time consuming it's going to be to run. Now, a very good work that people in US initiated is the DR modeling in WECC and NERC that has been used elsewhere in the world and adopted. But how we are seeing this, if in a country like Australia, so 40% of the generation is going to be the distributed PV and likes of rooftop PV, perhaps that level of modeling may not be sufficient. What level of dynamic modeling, for example, capturing the PLL or anything of similar nature that a DR uses to make it a more dynamic looking model, similar to a model of a battery or wind turbine or solar inverter. And in terms of analysis activities, I can't stop thinking of these two very important questions, that if we have a 100% or near 100% inverter connected power system, what is the correct share of grid forming and grid following inverters? Who is going to determine? And last but not the least, again, I'm just coming back to that chicken and egg status quo, that how we can breaking that status quo, that the equipment are designed to deliver the needs of a future power system, which we don't know. We know the needs of the current power system, and equipment manufacturer will need, heads up of many years basically to design, develop, and deliver these capabilities, especially if some of them will come at the extra cost. I think that's the end of this presentation. Thank you very much, and happy to take any questions.
All right, thank you, Babak. I'll jump to Slido for questions. Maybe before, while I'm working on it, can you speak a little bit to, I know IEMO has started looking into that need for more detailed models for synchronous generation as you start going into doing more detailed EMT studies and as you're getting less and less synchronous generators online?
Yeah, so I can basically share my views. So obviously my good friends at AIMO, they can, raise their basically reasoning, but I can only share, my view is that part of this is basically what I was mentioning, the interaction between the protection and stability. Otherwise, it's fair to say that the theory behind synchronous generator modeling hasn't changed. But if you're having a system with very few synchronous generators in perhaps now wrong part of the network, they would be more exposed to operating into their boundary conditions and extremities. For example, how close are you to loss of excitation, whether loss of excitation relay or out of a step relay could inadvertently be triggered because of operating under those operating conditions. So this is one thing that I can, definitely think of. And the other thing, which is not per se an EMT exercise, again, we don't want to overkill and fix every single problem with EMT, but typically in country that I live, or South America, the small signal stability has been another concern. Now, synchronous generators, the large one, always come with power system stabilizer. If many of them are going to retire, there is obviously a bigger burden on those remaining ones. But on that, I personally think there is a great application for battery energy storage systems to provide that pod application. But to answer this question, the most immediate application to me is more detailed modeling of protection system to be integrated into the dynamic model of the machine.
All right, thank you, Babak. Next, most popular question is, how can one model the whole system in EMT? For whole system model, you will have to simplify the network, which will then result in less accurate model.
Yeah, so what the approach that has been done is that you can break the network in as many parts as you would like to, basically. So the network, by which we mean like transmission lines and transformers, etc. So obviously there is nothing rocket science per se with them, so you don't need to necessarily use transformer saturation. If you have it, fantastic. You don't need to use geometrical modeling of the line. We're not using this for black start studies, but for stability studies. Network modeling, it's typically a very a straightforward conversion from the steady state load flow model that is coming. If there are dynamic model in the network, such as HVDC link, SVC, STATCOM, yes, that is correct. And the point that I mentioned in the very last slide, I agree. So there is basically a balance between how large the system you model. To me, everyone should have a base model in EMT, but whether you use that base model for each and every study you do, that I don't think is the right way of doing it. So that is one of the gaps that, as I mentioned in the last slide, how one can determine or an automated procedure essentially to decide which part of the network should be retained to basically run the studies more efficiently without losing accuracy.
All right. Next question is power factory acceptable for EMT simulations, or do you have to use something like PSCAD?
Okay, so I'm actually trying to be as agnostic as I can be. So, and like, obviously it's not, I'm not a person to determine whether it's acceptable or not, basically. So to me, all EMT tools can be basically applicable, and even a hybrid EMT and phasor domain modeling that especially people in mainland Europe are talking about because of the cross-border nature and who using what model. To me, Power Factory by default is and can be an equally capable simulation tool with regard to EMT simulation. But the point that I think Deepak was mentioning in one of his presentations earlier this year, so because, and it's an EMT model, is not basically act of God or is not considered by default basically good. To maximize the benefits of an EMT model, we should be using detailed model. Otherwise, you're running something very slow and not really gaining value. So the question that I'm, raising to my friends at manufacturing companies is that how many of them support these models in Power Factory or other simulation tool. If that is provided, then I would think that it's fair to assume that Power Factory, PSCAD, I don't know, HyperSim, you name it. And like I apologize if I forget any commercial brand, but I don't see there is necessarily any better or worse, because one is more widely used is not necessarily better, but again, it's a matter of convenience. So why we have been using tool X or tool Y in like US or Germany or Australia and not the other one.
All right. Next question is, to study voltage right-through curves, should it be done in EMT, or do you think it would be reliable to do it in RMS simulations or phasor-domain simulations?
So the country that I live, these studies are done in both tools, basically. So that is the requirement, because each one of them have their own merits. So we know that we cannot use EMT modeling currently to run a real power system in real time. If we have like 5-minute dispatch or 30-minute dispatch, you're not going to get meaningful, results within that 5 minutes or 30 minutes to run the power system. So therefore, the results from the phasor domain modeling should be sufficiently accurate. So you're not looking at subsynchronous interactions or really something unheard of. So if it's fault right-through capability, you expect reasonable accuracy from the phasor domain model. And then the EMT model is basically essentially to corroborate the results of the phasor domain modeling. So when more than a decade ago, I was working for a manufacturer, and I believe still most manufacturers doing it, is that when manufacturer design basic capability, it's always based on the EMT model, and then the phasor domain model basically derived from it. And now what I'm hearing from contacts on almost all OEMs of grid forming inverters, What we have been advised is that everyone start from EMT model. Sometimes even we have told that until an EMT model is not accepted, there is no point to develop a, according, phasor domain model. So to me, both have a place. As a design or as basically interaction studies, definitely EMT model, but phasor domain model also is still used in likes of dynamic security assessment applications.
Right. So the next question is, and you already commented a little bit on software, but I'll still ask. The biggest obstacle in performing EMT modeling is user-unfriendly software, combined with lack of subject matter experts to develop accurate models.
I actually I'm not trying to disagree with anyone. I'm trying to be as factual as I can be, and honestly, I'm completely unbiased, and especially being a consultant, really. And what I did not mention of that 20 years that I've been using EMT model, probably 14 or 15 years of which has been phasor domain modeling, even to the point of writing actually user written models. So I do like phasor domain modeling. Having said that, one thing and I have actually written user written model in phasor domain of I don't name again, phasor domain tool and EMT tool. So that's the most level of detail you can go. And I can tell you that again, this is different schools of thoughts, is not right or wrong. I found actually the EMT modeling basically more user friendly. And once upon a time when I started my career, so the EMT modeling, maybe there were like 20 or 30 people in the world that can do that. That's not the case anymore. So, and I find actually, for past 4 years, I have been, dealing with 30, 40 graduates or basically early career. So typically these people find EMT model easier to what they study in undergrad, like MATLAB Simulink or those kind of application. And it is, whilst it's fair to say that 20 years ago, yes, this was seemed very niche and there are only limited number of people, the majority of which in Canada, basically, that can do this kind of studies. That's not the case anymore. Again, what I can share with you, that at the time that we, myself at AIMO decided to do this type of modeling, 95% of which was done basically in-house. And we knew EMT modeling, but we weren't the most prominent expert necessarily, or maybe one or two people. But it has been done. It has been successful, and I'm very pleased to see still my former colleague at AIMO basically taking it to the next level. So don't necessarily, that's not my view, and I'm happy to be corrected that I don't think that this is like person that does EMT modeling come to the earth by God and it's has superior capabilities to the others. So that's not my view.
Right, thank you. I think I'll ask one last question and then we'll wrap up. From your experience, can you speak about how to combine phasor domain and EMT models and simulations?
Okay, so I need to be upfront. So this is a topic that I have been following with interest, but I'm not necessarily an expert. We haven't done, always this has been on the table. We basically didn't do that, but it is, and I mean, like we are considering now actually, because previously the application of these EMT modeling have been to operate the system or basically to look at generator interconnection studies and like fault right through that you were mentioning. Now, as we are getting much larger clusters of inverter-based resources, and that say 10 gigawatts of wind and solar in a radius of say 100 kilometer in a system that its whole demand could be like 15 gigawatt. So this very clearly tells us that maybe the rest of the system is not that significant, but you still need that because what I have personally learned with putting boundary buses incorrectly or applying incorrect assumption, the results may be inaccurate. So this is one key application that I can see that we don't need to model the whole system in EMT. Whether we can use the phasor domain model for modeling the rest of the system, and especially if one of the questions that we're trying to answer is the impact on small signal stability modes, so these are really the electromechanical modes of oscillation that might be changed as the system and synchronous generators and the interconnector flows are changing and interconnectors are being added. So this is an application I see. And like I said, I'm seeing that my basically colleagues and friends in Europe in particular, considering this. I have not seen in North America. It's not been done per se in Australia. We are considering in Europe. There is a very good reason, because I mean, if you're looking at Germany and France and Belgium and Netherlands, so you're not probably interested in all of them. So, and all these models are by default available in basically phasor-domain. So if you're looking at your neighboring country, especially big neighbor like France or Germany, do you need to model everything in basically EMT? Or perhaps you can let the phasor-domain model to dynamically and instantaneously tell you what the equivalent source is going to look like, rather than you try to simplify the equivalent of France or Germany by Thevenin source, which is going to be most likely incorrect.
Mm-hmm. All right, so we're at the top of the hour, and so going to wrap up. I would like to thank Babak for his really informative presentation and the audience for attention and great questions. As I mentioned earlier, an email will go out once the video file has been posted, and we'll answer all questions that we didn't get to and get them posted as quickly as possible as well. On May 31st, ESIG and Lawrence Berkeley National Lab will jointly launch a webinar series on reform of generator interconnection processes with the first webinar on interconnection study criteria, with featured speakers from Lawrence Berkeley National Lab, Nextera Analytics, Electric Power Engineers, the Brattle Group, and NL Green Power. I would also invite you to attend our upcoming workshops on meteorology and market design, as well as special topic workshop on grid forming inverters in Denver the week of June 6th. The week of June 6th. And Ryan linked up the registration links and links with more information in the chat. Further information of all our webinars and meetings can be found on our website, www.esig.energy under events, and in our newsletters and information emails, and you are all invited to attend. Babak, once again, thank you so much for a very timely and informative webinar, and thank you all for your interest. We look forward to seeing you again in the near future, and in the meantime, everyone, take care, stay safe, and thanks for your participation. See you soon.